Today, we're moving on, and we're moving into what's really happening with those electrons, right? And I framed this on Monday by telling you that the Rutherford atom wasn't going to make it more than 10 to the minus 11 seconds-ish. Right? Because classical E&M would tell you that the electron, if it's going around like this, is radiating energy, and so it spirals down into that positively charged nucleus. So Rutherford got it right in the sense that, you got all this positive charge concentrated in this one tiny little volume in the middle, and the electrons are way out there. That's the planetary model, but we needed some new theory to understand why the whole thing was stable, and that's where Bohr comes along, and that's what we're going to talk about today. Now, we need to feel our oneness with waves. Okay, now I think probably most of you know about waves, but since we're going to be talking about them a whole lot today and as we go forward, I want to make sure we're all on the same page, right? So here's a wave. Well, we know about water waves. They move a meter a second. Sound waves a little faster, right? And you got these characteristics of a wave, right? The frequency of the wave, right? The wavelength. And so I just want to make sure that we're all together on this because we're going to be talking about these variables a lot, right? So if you have like a wavelength, that might be in meters, right? How many meters do you have per wave? Okay, we're getting somewhere here. If you have the frequency, and I'll use this notation here, you could use F. You might see F sometimes. I like using nu. And if you have the frequency, well, that's going to be the number of waves per second, for example, right? And so the speed is going to be the two of them multiplied together. Now, I know a lot of you have seen this, but again, I want to get it up here. So it's going to be meters per second if these are the units that I'm using, seconds and meters, right? Okay, now, if you're light, as in light, then you have a speed that is a constant in vacuum, and we know that, right? So the speed of light, right? So for light, let's put that right underneath. For light, okay, the speed is c, which equals 3 times 10 to the 8th meters per second. Okay, just getting some good stuff. So if I wanted to know, for example, how to go back and forth between frequency and wavelength for light, well, I can just use this relationship, right? So let's put an example up there, right? So, So for example, if you're like red light, okay, so if you're red light, then you might have a frequency of around, let's say 450, there's a range, but 450 terahertz would be a frequency, okay? And so now I can get the wavelength because I have that relationship. So the wavelength for red light is c over nu, which is going to be equal to 3 times 10 to the 8th meters per second divided by 450 times 10 to the 12th per second, right? That's the measurement of hertz is 1 over seconds, right? That's frequency, right? 1 over seconds. Okay. Now, that gives me a number that's pretty, it seems like it's pretty small. 0, 0, 0, 0, 0, 0, 6, 6, 7 meters. And so we could use a different unit like nanometers, right? Which is just 10 to the minus 9th. So we could call that the wavelength of red light, 667 nanometers. Now, I'm doing this all slowly and carefully because we're going to be doing this a lot, and so I want to make sure that you're comfortable with this, and we're going to add something to this in just a minute. So that's like, oh, if I was blue light, where's blue light? Let's put blue light. I'm going to leave red light here, and we'll put blue light right above it so that you can see them together. So blue might be something like, a frequency of 650 terahertz, so higher frequency. And that would give you a wavelength of something like 460 nanometers. I'm putting these both here because I'll be comparing other aspects of these colors later. Okay. Now comes back. Now that's our oneness moment with waves and light, and now we come back to our story, our detective story of what's happening inside of atoms, right? And it really requires us to go back. I said Bohr had some postulates about quantization. There was work going on at the time already related to quantization, okay? Now, so I want to share with you that work because it's what inspired Bohr, and then we'll do the Bohr model, but also I want to get you thinking about what this all means, right? So if you think about music, like you can think about these two instruments, this might feel like, the violin might feel like something where you can just play continuous notes, whereas here you can't, right? It's discrete, what you can play. I can't play any notes in between, right? Something is discrete, it's quantized. Well, that's pretty obvious, right? You look at those, you're like, yeah, okay, that makes sense. But what about, there's some things that aren't as obvious, like here, oh, notice what's in the calendar, right? That's a screen. Now, a screen from far enough away might not look quantized. But then when you look up, you look at it closely, it is. It's pixels. There's nothing in between. There's nothing in between. Now, the thing is that these people, at the time, people thought about the world in a certain way. There's some things where it's just like obvious they're violins, like light. And then they're like, wait a second, these things are acting like xylophones. What's going on? And that's really what, so Planck's contribution was really, he was one of the first kind of deep thinkers to talk about quantization, and it was quantization of light. It was quantization of light. And so what he said, and this is together with Einstein, and I'll show you what Einstein did in a minute, so it's called the Planck-Einstein relation. And what he said is that the energy of a photon, so Planck, why did I just go all caps? I don't know. I don't know. There's a reason. Planck-Einstein, he said, they said that the energy for light, the energy is related to the frequency through a constant. And so in particular, E equals H times the frequency. Now, this was revolutionary. It might just look like a simple relationship. Oh, and by the way, this is a constant named Planck's constant. I'm going lowercase. Planck's constant, and it like other constants, it has a value that doesn't change. So that value for Planck's constant is I'll give it to you in two different units, so we have it up here, 6.62, sorry, 626 times 10 to the minus 34 joules second, okay? Or it's also equal to 4.136 times 10 to the minus 15th electron volts seconds. Notice the units are in energy times time, Planck's constant. Okay? I mean, and you can see that it must be because this is energy and this is 1 over time, right? The frequency. So it's got to have those units for that to work. But this, did I make a mistake? No. I'm worried. The dates are still hitting me hard. I'm still thinking about that. Having nightmares. 100 years off, 90 years off. I'm good. So what this told, what they saw is that, light had a frequency, but it also had somehow this unit of energy, a unit, a discrete unit of energy that you can now calculate using Planck's constant, right? And that was revolution. That was not what people thought. And it really all came home in what Einstein did, which was what the experiments that he won the Nobel Prize for. His deeper thinking was in relativity, but he won the Nobel Prize for this because it was absolutely essential to further this idea of quantization and show it with an experiment. And because it was so important, I want to share that experiment, because what Einstein did was really quite amazing. He shined light on a metal. And what he saw, so this is called the photoelectric effect. Photoelectric effect. And this is where you take a piece of metal, okay, and they knew there were electrons in there, right? That discovery had happened. So they knew there were electrons. And they also knew if you hit this metal with energy, the electrons could come off. I mean, after all, that's what the cathode ray tube was, right? It was electrons coming off of a piece of metal. And in that experiment, you hook up a voltage, but here he shined light. And so if you take, for example, different frequencies of light, and you shine them on this same piece of metal, so let's go red, and then let's go green, and then let's go blue, right? Now, if you shine red light on the metal, nothing happened. Nothing happened. I mean, okay, we know if you just crank up the intensity of the light, something's got to come off. You're putting all this energy. No. Why? Because the particles, the packets, the quantized amounts of energy that kind of light can have is determined here. So what Einstein says, well, okay, then these must be particles. They must have some energy associated with the particle that follows this relationship, E equals h nu. And notice that doesn't depend on intensity. It just depends on frequency. So I might be hitting this metal with more and more of them, but each one only has the same amount of energy limited by that relationship. So if I want to hit those electrons with more energy, I got to change the frequency, right? And so what was found in this experiment is that, well, maybe here you get nothing. So here you get nothing. How am I going to write that? No, okay, nothing. I just won't write it. Here, maybe you get electrons, and here, maybe you get faster electrons. Right? Electrons, because these have these fundamental particles of energy of light have different energies, right? So now we can calculate it. We can calculate the energy of that red light, and we can calculate the energy of the blue light, right? Because I have now E equals h nu, and if I plug it in, which I won't do, you get something like 1.8 electron volts. And if you do the same thing for blue, you get, from the Planck-Einstein relation, you get the energy is 2.7 electron volts, right? So what Einstein did in this experiment, which was so crucial, is he measured, he changed the frequency of light that you shine on this metal, and what he saw is that there was nothing, 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 and then all of a sudden, you literally had, if you plot the kinetic energy of the, I'll write it out here, ejected electron, right? So that's what's being plotted there. Then, and you plot that versus the, I said I wasn't going to use F, versus the frequency of the light, nothing, nothing, nothing. And then all of a sudden, there's a linear relationship between them. That explains it. Because these things were made of these particles that were called photons, right? So, photons. Now, while this was blowing their minds and winning prizes and all that, Bohr came along. Now remember, this is what I mean by dates. Okay, apart from the dates, okay, we know now there was a lot of time between those experiments, especially Dalton and Thomson. And that's where we were on Monday, right? But so Bohr was looking at all this. Remember, he wrote the paper where he said it is It is with great interest the Rutherford atom, meaning it's wrong. It needs fixing. Meanwhile, Bohr's looking over at Einstein and Planck, and he's like, wait a second, let me get some of that quantization stuff. Because, you know, if it works for light, what if it also works for electrons? What if it also works for electrons, right? And so he's looking at this stuff going on with Planck and Einstein, and he applied it to the electron in Rutherford's atom. That's what he did. That's what Bohr did. He said, you guys got your light thing, I'm going after the atom, and what I'm going to do is I'm going to make actually a fairly simple postulate. Why is that up there? Let's go. I'm going to say that for me, the quantization is going to happen with the angular momentum. So Bohr came along and he said that the angular momentum of the electron, so L equals mvr, right? Remember, we listed the Bohr postulates, and one of them was that Newtonian mechanics would hold. Angular momentum, mvr. But there's something added to it. He said that that angular momentum could only have discrete values, quantization. So he said that this is quantized, and he was specific. He said it could only be some number, some integer, times Planck's constant divided by 2 pi. Why not? When in doubt, divide by 2 pi. Right. As you all know, that has to do with just making math easier. Now, that's the angular momentum, and he said it's quantized, and n is the key here, right? Because n is this thing that says that it must be some unit, right? This is like the unit. It's like that photon energy, right? It comes in units, and so, but it comes in units of integers, right? So you could have 1, or you could have 2, or 3, but not 1.5, right? That's quantization. So n had to be 1, 2, 3. It had to be some integer, and here we go. Watch this. We're going to call it a quantum number. Oh, I should have written that in all caps. Quantum, thank you for that. It's our first quantum number, and we've only known each other for a week. A week. Here we are. We're quantizing things. Quantum number, because it's a number that counts quantumness, quantization. This is how you get the quantization from this, so it's a quantum number. Now, here's the thing. I will not derive Bohr's model for you. I will tell you what it is. And if you want, you can look up the derivation. It's actually really fairly straightforward. You know, it basically has to do with this one assumption, quantization of the angular momentum of that electron, combined with F equals ma, and the electron is stable. It's not accelerating in, right? And when you do that, what you get, let's put this, no. Let's put that back up. So what you get with Bohr's model is the following. You get 3 extremely important outcomes, okay? First, you get that the radius of that electron is quantized. Then you get that its energy, the energy that it's allowed to have, is also quantized. And finally, you get that its transitions are, you got it, thank you, quantized.